Let's do an example of getting an error bound for the midpoint rule. In scientific, advanced scientific work or engineering, you would use something at least as complicated as Simpson's rule, or you'd use some package that you don't necessarily know exactly what it's doing in practice, but the same ideas apply to those more complicated rules. And for the midpoint rule, it's going to be easier just to see what's going on. So we're going to look at the midpoint rule. So our goal specifically is we've got an integral 0 from 2 to 5, of dx over ln x. This is one of the many integrals where you just can't express the antiderivative in an elementary form with polynomials and e's and roots and things like that are familiar. And so the best way to do this is some sort of numerical method. And we'd like to get an approximation. We'd like to say that absolutely guaranteed we know that's accurate to within, let's say, 10 to the minus 4. So roughly 4 decimal places, but let's just say, to be precise, the error should be less than 10 to the minus 4. So we've got a great tool. This is not the only error estimate you could come up with, but it's the simplest one. It's the one that's in most books. If you happen to know that some sort of upper bound on the second derivative of the function on the interval in question, then the size of the midpoint error, we might be able to say something about which direction it is, but let's just talk about the size right now, is less than or equal to that bound over 24 times b minus a cubed over n squared. So in order to apply that, the only problem is we need to have some sort of upper bound. We need to find k, some upper bound for the size of f double prime on 2 to 5. If we could find the exact maximum of that, that's great, but I'm going to show you how you don't need that. Often you can be pretty satisfied with just a rough upper bound. Okay, so let's calculate the first and second derivative. Okay, so f of x here is 1 over ln x. So f prime of x, you can use the quotient rule, or really it's the simplified form of that's the reciprocal rule. It's going to be minus the derivative of the bottom, and that's just 1 over x, over the bottom squared, ln x squared. And that's like sine and cosine and things like that. That's actually usually written as ln squared x. Same kind of thing. Okay, so now that wasn't too bad. Second derivative, got to use the reciprocal rule again, but then there's a product of things on the bottom. So let me just write out the reciprocal rule. It's minus the derivative, so minus the derivative, oops, I wanted a fraction over there, yeah, minus the derivative of that x 1 squared x. Oh, and there was already a minus in front, so the minus is actually going to cancel. Okay, so we're going to get the derivative of the bottom over the bottom squared. Okay, now we use the product rule on the top, and derivative of x is just 1. So we're going to get just that, just the second thing left alone, plus x, oh, now we need a little chain rule, times 2 ln x times the derivative of that, 1 over x. Okay, so a little complicated, but notice that, let me expand the bottom here a little bit. That's x squared times log fourth, and we get a little bit of cancellation. That's always what happens when we take a second derivative of something that already was a quotient. You're always going to get at least one power canceling. So I'm going to cancel out those logs with one of the logs down here. Oh, and conveniently enough, this x cancels 1 over x. Really not so bad. Okay, so there's the formula for the second derivative. It's not ridiculously weird. It wasn't super hard to get. But now what we want to know is on the interval 2 to 5, that's all we care about right now. How big can this be? And I'll show you a little bit more accurate estimate using just a computer graph, but suppose you were still trying to do as much as possible by hand. One thing you can do is you can look at every piece of this and just look what's the worst case scenario for every piece, and then put them together. So on 2 to 5, we know that, well, certainly x is less than or equal to 5. Ooh, except wait a minute. It's in the bottom. So the worst case scenario for a fraction, if we want to see how big can this be, the worst case scenario is actually where x is small. So it's really, the key is that the worst case scenario for x here is 2. So I'm going to actually put in worst case is when it's equal. Because inequalities are great, but sometimes it's easier to think of in terms of like just worst cases, because that gets you to equalities. Okay, what about ln x? Now that's in the bottom as well. Okay. Well, ln x, when I increase x, the log increases. And so the worst case here is, again, since it's in the denominator, the worst case here is when the log of x is small, and therefore when x is small again. Okay, so log of x is going to be less than or equal to, sorry, this is greater than equal. I don't know why I switched. Okay. Log of x greater than equal to, that must have been confusing. Log 2. Okay. Another way to say it is the worst case. The thing that's going to make that fraction the biggest is where log of x is smallest, and that's where, yeah, log x equals log 2. Okay. Ooh, I don't want to go quite so far. And then on the top, you've got a log x plus 2. The worst case for that is in a different place. The worst case for that is where x is as big as it's going to be. Okay. And the top, the numerator, well, let me make that not math. Log x plus 2, okay, that's going to be less than or equal to log 5 plus 2. Or in other words, worst case is the numerator is equal to log 5 plus 2. So you might be thinking, it's a little bit weird that we're plugging in different endpoints of the interval for the different parts, but it's all about taking each separate piece and looking at the worst case scenario given the role it plays in f. You might also say, look, I can't simultaneously have the worst case scenario for the numerator, where x equals 5, and the worst case scenario for the denominator, where x equals 2. So this is going to be a generous overestimate for how big f double prime can be, but it's going to be easy to get. And I'll show you a little bit better thing just from graphing the function. But this is a fairly common thing. So the punchline is that the size of f double prime, and notice f double prime always, well, let's not worry about that. Let's see. It's, well, yeah, it's always positive. Let's get the powers right. It was x squared and log cubed. Okay. The worst case is I put in the worst case for the top, that's ln 5 plus 2. I put in the worst case for the bottom, that's 2 squared, and the cube of ln 2. Okay. And then I just need to calculate that. So that's something that's not super sophisticated. Wouldn't need a graph or anything, just need a calculator. And I'll go ahead and do that numerically. And it's about 2.7. Okay. And let's say 2.7, let's say 2.8 just to give it a little bit. Oops. A little bit of wiggle room. Okay. So let's see, I had done a previous calculation. Oh yeah, I wanted to show you, you know what, I'm even going to give it a little more wiggle room just to make things simple. I'm just going to say 3. Usually when you have an error bound like this, it's not going to kill you if you just make it a little simpler. And you don't have to do that, but okay, so I just checking the calculations, yeah, so pretty much the same kind of calculations around here. Now, if you really wanted to be a little tighter and try to be a little more efficient, you could actually just graph this function and note that the biggest it ever gets is at 2, and that's just about y equals 2. So we could have, with a little bit more effort with the technology, we could actually replace this 3 with a 2. But it's kind of nice to know, a little lower tech, we were actually able to get a bound. Okay, so depending on the exact problem, you'll be led to one way or another. Okay, so the main thing is that we now have k. K, we're going to use k equals 3, because I want to pretend that we didn't actually go to this level of technology. And we put that in. The 24 is locked in on the formula. B minus a is 5 minus 2, or 3. That's cubed over n squared. And we want that to be less than or equal to 10 minus 4. So this is a very common place to get to. Once you have your k, the n is up to you. It's how much work are you willing to do, or how much work do you feel like you need to do to get your error estimate. So we're just going to solve this inequality. Okay. So if I just multiply by n squared and divide by 10 to the minus 4th, and I'm just going to switch the order, what we need is that n squared must be big. We should always get this inequality that says n or n squared must be bigger than something, because we're saying what's the minimum amount of work we need to do to get a certain error estimate. And if you just do the math, it turns out to be about 184. Again, if you want to make things simple, just make it 200 or something if you want. It's not a lot more work, but I'm going to use the 184. So that's the first really big way station. It says, hey, here's how big n needs to be to absolutely guarantee that the midpoint approximation to this integral is going to be within 10 to the minus 4. That's cool. Then you could hand it off to somebody who actually does midpoint rule, but let's go ahead and do that. We know that. Okay, so what is the midpoint rule? We need to do a few preliminary calculations. The delta x is always crucial for any uniformly spaced integration rule. It's 3 over n, so that's going to be 3 over 184. I'm just going to leave it like that. The midpoint rule, remember, you start at 2, you start at a, and you scoot over by delta x's and k delta x's, but then you backtrack by 1/2 delta x. This is just exactly 1/2 of delta x to get it in the middle. Alrighty, and now we are just going to put that in. I pre-calculated it here. So the midpoint with n equals 184, it's delta x times the sum of the function, which is 1 over ln x, evaluated at those precisely carefully evaluated xk bars. If you just do that summation, that's definitely something where you want a calculator or a computer. Turns out to be about 2.589414. That's really where you would stop. You can say, without any other knowledge, anything more sophisticated, you can say that is going to be within 10 to the minus 4 of my answer. And probably better because I did some sort of generous overestimation of the error. Remember that if you had done the more accurate error estimation, we could have had a 2 right here instead of a 3. So the error is actually guaranteed to be 2/3 or less. And if you actually look at this f double prime, most of the time on this interval, f double prime is a lot less than 2. So that gives us a hint. You know, this is actually going to be probably rather better than our worst case bound on the error. But it's nice to get a relatively simple and absolutely rock solid guaranteed bound. Now, it turns out if I let the computer that I'm working on here do its preferred numerical integration routine, which honestly I don't know exactly which routine it uses, but it's something a bit more sophisticated, it gets 2.589425. And if you subtract those, the error is actually starting to appear in that 5th place. It's about 10 to the minus 5th. So it turns out to be about 10 times as good as our guarantee, but the guarantee was nice to know, and we didn't have to do anything more sophisticated than what we have with the midpoint estimation theorem.